Welcome to a SimCenter AimSim Student Edition tutorial discussing how to translate an experiment done in real life into AimSim to further understand its behavior. The experiment chosen is that of a fire syringe, which is an actuator containing a small tuft of cotton at the bottom. To perform the experiment, a person needs to apply a force that will move the piston down fast enough, where the air within the chamber will compress and increase its temperature to a point which will ignite the cotton within, as shown in the video. While working within this model, AimSim platform features of CAD import, green design, cross results, and batch runs will be utilized. Once complete, the speed and force needed to close the piston can be found, as well as the heat transfer behavior for the process. In AimSim, the model used begins with a single pneumatic chamber, single rod jack with spring assistance component from the pneumatic library. This component will reflect the syringe with the chamber and air within corresponding to port 1. From here, a convection exchange component from the same library is attached that will reflect the heat exchanged between the chamber air and the cylinder wall. The cylinder wall is characterized by the thermal mass component that is attached to another convection exchange component to reflect the heat transfer between it and the external air. The remaining thermal mass ports can be plugged. Port 2 of the actuator is associated with the piston, which will be moved by imposing a set displacement from the converter of velocity and displacement from the mechanical library. A piecewise source is fed into the displacement port, imposing a path to move the piston. Additional components needed include a gas definition component, a thermal solid properties component, and a constant source with a signal sink that will be used later after simulation. In submodel mode, Premiere Submodel is acceptable. In parameter mode, let's first look at the actuator component that requires parameter values for various physical dimensions. CAD models for the assembly are readily available, and dimensions can be pulled directly from it using the CAD import tool. With the tool open, both the piston and cylinder parts are brought in as step files. The measurements needed are titled and listed within the measurements window, and can be selected to see their location within the model. For easy reference in AimSim, each of these values was assigned to a global parameter by copying and pasting their values into them, with tags assigned to denote that they're from CAD. And with the global parameters completed, the actuator components parameters follow as such. Be sure to multiply the piston and rod radii values by 2 for the respective diameters, and in addition, set the spring rate to 0, as there is no spring used for the real syringe. For the dead volume, the portion containing it within the chamber is a hemisphere with the same radius as the chamber. The expression for the volume of the shape utilizing the chamber radius global parameter is entered. Also, the unit for the initial condition parameter for temperature is changed from Kelvin to degrees Celsius. This is done to make it easier to determine when the needed temperature for the cotton to catch flame is reached, which is given as 210 degrees Celsius. The value for the thermal exchange coefficient is also lowered to 0.22 to better reflect the behavior of the system. This value was determined through trial simulations similar to what will be done to determine the minimum speed. Make sure to take note of any units that have been adjusted, shown in bold. For the first convection component between the chamber air and cylinder, change the calculation type to cylinder with predefined correlation. The length and radius can be set to the respective values for the chamber. Looking at the thermal mass component, this will represent the cylinder and can be assigned to correlate to the volume value pulled from CAD. The last convection component will have the same calculation type, but with the length of the cylinder and radius being the difference of the cylinder and the chamber. The piecewise source dictates the behavior of the system by setting the time in which the piston closes from the top of the chamber to the bottom, with 0 being the initial position, since the piston displacement parameter within the actuator is set to the length of the chamber. The number of stages in the source is set to 4, with stage 1 being from 0 to 0.05 meters in 0.01 seconds, then held at 0.05 meters for 0.04 seconds, and then pushed down to move from 0.05 meters to 0.19 meters, which is almost the entire length of the chamber. The time for stage 3 is assumed to be 0.1 seconds for now, but will become the value to be evaluated in a batch study to determine the slowest speed to close the piston to still achieve combustion of the cotton. Stage 4 will then be from the closed position at 0.19 meters and move up to the top at 0. Moving to the material properties component, starting with the gas definition, the fluid definition can be entered as air, and the properties definition as real calculated with van der Waals equations. The thermal solid properties definition must be user-defined, with the type being constant values, for the cylinder is made of polycarbonate, which is not available within AIMSIM. Through research, the values for density, specific heat, and thermal conductivity can be entered as followed, with an option to assign the name of the material last. The constant source added will serve as a benchmark. The source output is entered as the goal temperature value of 210, providing a method to visualize and analyze results for the minimum speed to close the piston through cross results. With parameters complete, the next step is to establish a batch run. To start, let's bring in the time for stage 3 of the piecewise function as mentioned earlier into the study parameters window, and move to the studies tab. The study definition used will be varying between two limits, with an initial value of 0.1, a step size of 0.01, and number of values below as 8 and above as 0. This will create 9 runs with the values shown, ranging from 0.1 to 0.02 seconds. Press OK to confirm these parameters, and move to simulation mode. Now in simulation mode, open the Run Parameters window, where the simulation final time needs to be changed to 3 seconds, which is plenty of time to capture the physics of the system. Also, change the simulation type to batch and run the simulation. After completing the batch study, one could analyze results plots to determine the most amount of time the piston could close to achieve combustion. A faster way, though, includes using cross results. Cross results help to evaluate a particular results variable across a batch study at a particular instance. For this demonstration, we wish to determine the highest temperature each batch run achieves across the simulation, as the slowest time with the highest maximum chamber temperature will be the desired value. To start, make sure both post-processing and cross results are available through the Edit and Show/Hide menu. Drag the results variable for temperature at port 1 of the actuator component into the post-processing window. Within the expression field, add the operation LOC-MAX, short for local max, to the beginning and place the variable name in parentheses. This creates a variable that displays only the highest value for each of the batch runs. Now, rename the variable maxTemp and move to the cross results window, where the output of the constant source can be dragged and dropped in. To add the post-processing variable, right-click in the post-processing window and select Add. Scroll through the list until you see the variable named maxTemp and double-click. From here, highlight them both and drag them into the window. The plot shown has both the constant source output and maximum temperature within the chamber for each run side by side in bar graphs. Now it is easy to see which of the runs reached the desired temperature and which didn't. The ruler tool makes it possible to see each of their respective values, and determining that run 7 is the last run that meets this requirement. Opening the Select Results Set menu and displaying values, run 7 is shown to be a value of 0.08 seconds, which will be our set value for stage 3 of the piecewise source. With the desired time entered, a single simulation can be run to analyze the force required to push the piston down in time. Along with changing the simulation type to a single run, let's enable green design settings found under the Standard Options tab. Adding elements of power, energy, and activity as variables within the components enables us to see how energy moves within the system. When activating these 3 variables, the model will need to recompile, and then another simulation can be run. After the simulation is complete, the force required to move the piston can be found with the results variable for the force exerted by the actuator rod variable within the actuator component, whose peak is around 131 newtons. The heat flow from the air into the cylinder wall can be evaluated within the corresponding convection component, or through the newly created power variable within the thermal mass component. The energy and activity of the thermal mass can be displayed as well. With the required speed and force, as well as the heat transfer behavior found within the model, this tutorial has concluded. Thank you.